Okay, so we're going to be doing the tutorial 9 for csc165. So what you do here is, so we take a look at this function, and here, so whatever we input, n becomes. Here, let me just zoom in a little bit. Okay, so let's take a look at this. So you can pause for a second to see for yourself. But first thing that happens is that whatever n is, it gets set to x. And so next we look at this loop here. In this loop here, we notice that this is going to continue as long as x, which is equal to n, is larger than 1. Okay, so the thing that's deciding this is going to be the x variable. So next we look into how exactly x changes. Well, x can change in two ways. X, in this condition, x will be divided by 2. This condition, 2x will be subtracted by 2. We can see here that, already, obviously, this condition here is going to be terminating faster. So it's bringing us closer to termination. And this one is going to be lengthening it. So if we're thinking about worst case, then probably we want to always hit this condition, and the best case probably always this condition, maybe eventually hitting this condition. So okay, so that's a quick look at the code. And yeah, so this condition is true whenever x is even. This is to say that x can be divided by 2 with no remainders, so same as even, and then otherwise it's this. Okay, so they're asking us here to say that we want to show what exactly happens in 3 loops. So we want to see what we know in 3 loops. Okay, so let's quickly think of the possibilities of what x can be. So since the deciding factor is whether it's even or not, okay, so here we want to show that after 3 loops, 3 iterations, x decreases by at least a factor of 2. So what we want to show is, after 3 iterations, x becomes at least 1/2 of x. Okay, so when we consider the cases, since this is going to be, how x changes is affected by whether x is at the time even, we're going to be thinking of a couple cases. So let's think about it here. So let's say case 1. Let's say that x is odd, right? So x, you start off here, and I'll just put odd below so we can keep track of it. And then this is iteration 1. Okay. And so x is odd, which means that x becomes 2x minus 2. Okay. And we note that this is, you can factor out the 2 here, and you easily see that this is now even. So then in the second iteration, it becomes even, so then x gets divided by 2, and this whole value is x, right? So you have 2x minus 1 divided by 2, which is equal to x minus 1. Now, x minus 1 is, x is odd, so x minus 1 is even. And then we go through the third iteration, and what do we have here? So this is even, so then that means x minus 1 gets divided by 2. So you have x minus 1 divided by 2. Yeah. And so you can rewrite this as x over 2 minus 1/2. And, this is less than or equal to 1/2 of x. So in this case, what we're trying to prove is true. Next, let's start to look at what happens when x is odd. So let's say x, or rather we already looked at what happens when x starts off as odd. Let's think about x is even, but x over 2 is odd. Okay, so we start off as x, which is even now. In the first iteration, we see that, what do we have? So this is even, so that we get x over 2, which from here we see that it's odd. Okay, second iteration, it's odd, so you end up putting a 2 over everything and minusing 2, which is equal to x minus 2. X minus 2, x is even, so this is even. Then we go to the third iteration, and x is even, so it gets divided by 2, so you end up with x minus 2 divided by 2, which you can also rewrite as this. And again, what we wanted to prove, it holds. Yeah? Case 3, and I think you probably know where this is going. So x is even, x over 2 is even, but x over 4, or x over 4, and when I'm talking about x here, I'm talking about whatever value at this point, x. So x is changing. X is not the same x. So that we're clear, because the tutorial answers, they kind of do it differently. I prefer to think of it like this. It's a little bit more clear to me. So x over 4 is odd. So x starts off as even. First iteration. Okay. So same thing as before. X over 2. But the difference being x over 2 is even. Right, so this is even. Now the second iteration. Since it's even, it gets divided by 2 again. X over 4 is odd. So since it's odd, in the third iteration you multiply by this, minus 2, which is equal to 2 x over 2 minus 2. Again, smaller than or equal to half of x, the original x. And then let's consider the last case. X is even. X over 2 is even. X over 4 is even. So you have x is even, first iteration, even, second iteration, even, third iteration, even, which is smaller than or equal to 1/2 of x. So in all conditions, after 3 loop iterations, we know that x smaller than or equal to 1/2 of x. Okay, so we're asked to find the upper bound of xk in total iterations that will run for the upper bound of the runtime of f. Okay, so if you think about it here, we're asked to find the asymptotic upper bound of f that's better than whole than. So this is what we're looking for. We're looking for the worst case, it seems to me. In the worst case, we'll be analyzing code. So again, as a reminder, it's very helpful to know this. The worst case O, which is this line here. This will be code, and then the worst case omega will be a family of inputs. Same thing with, so if you have the best case O, that'll be a family of inputs. Best case omega would be code. Okay, so here we're looking for this. So we let k be a natural number. Let xk be value of variable after 3k loop iterations. Okay, so let's think about what we have. We know that at, okay, oops, pen's not working. Okay, give me 1 second. Okay, the pen's working again. Okay, so 3k iteration. Okay, so what do we know? Okay, so if we say x of I, where I is number of iterations. Okay, so what do we know about x of 0? X of 0 starts off, the input is n. So it equals n, right? We know that x of 1, from what we proved above, is going to be smaller than or equal to n over 2. X of 2 is smaller than or equal to n of 4. So, okay, we can do one more. Smaller than or equal to n of 8. Okay, which is equal to, okay, so we can think about this as 2 to the 1, 2 to the 2, 2 to the 3. So x to the k is going to be smaller than or equal to n 2 to the k. Alright? So we know that, we take a look at the code up here. So the loop runs when x is larger than 1. Loop runs when it's larger than, x is larger than 1. So it terminates, and all you have to do is negate this, and x is smaller than or equal to 1. Okay. So we want to find what the smallest k is for it to terminate. So this is the same as to say when x of k is smaller than or equal to 1, which is the same as saying n, we want it in relation to n, n2k, which is what we got over here. Okay, now it's just an inequality and we just do some math. So we take, we multiply 2k, take log 2k, this is equal to k log 2, and since I didn't specify but it's going to be in log 2, this becomes 1, so you have log 2n smaller than or equal to k, so k equals log n is the smallest number of iterations for a program to terminate. Right. And then we need to write since each iteration counts as a single step, the total runtime is actually, so the smallest k, you need to put a ceiling there because, you know, the number of iterations has to be a whole number. That's not a big deal because it runs in ceiling of log n, we know that it is in the big O of log n itself, because ceilings and floors, they don't really matter in regards to big O, and there's a theorem on that somewhere. Okay, so that's question 1.